Hello everyone. Today we'll be discussing the topic of the structure of glucose from the chapter of biomolecules. I start the screen share. So glucose is an aldohexose. Aldohexose means it has an aldehyde group and it has 6 carbon atoms in its chain. It is one of the most abundant compounds which is found in nature. Okay, it is found, all of you know, it is prepared in plants by the process of photosynthesis. So in nature, it is found in free state as well as the combined state. Both the states, free state and the combined state. Free state means it occurs in fruits and in honey. Combined state, it occurs in cane sugar, starch, and cellulose. Okay, these molecules are the polymers of the glucose. So next is, how do we determine on what basis the structure of the glucose was determined? It was based on a few chemical reactions that were carried out on the molecule. So on that basis, earlier the structure was ascertained. So the first of them was, what were the evidences? The first was the molecular formula of glucose was found to be C6H12O6. Then the straight chain structure of glucose was ascertained by this, was obtained from this reaction. That is, when you heat glucose with HI, what happens? It undergoes reduction. HI is a reducing agent. So it forms N-hexane. As a result, what is formed? N-hexane. That is a straight chain hydrocarbon containing 6 carbons. So what does it suggest? That glucose contains 6 carbon atoms in its straight chain, all arranged in a linear chain. Next is the presence of 5 hydroxyl groups was obtained from the evidence that when you heat glucose with acetic acid, it forms a pentacetate. Okay, hydroxyl groups react with the acetic anhydride to form a pentacetate. So pentacetate means how many OH groups are present, how many hydroxyl groups are present. There are 5 hydroxyl groups. Okay, so next is the presence of carbonyl group was ascertained by the reaction of glucose with HCN. Carbonyls, we have done it in the chapter of aldehyde, ketones and carboxylic acids, that carbonyls react with HCN to form cyanohydrins. This is a cyanohydrin. Same happens in glucose. So you call it glucose cyanohydrin. Similarly, it reacts with hydroxylamine to form oxime. So this is called glucose oxime. So both these reactions show that glucose contains a carbonyl group. Next is the presence of an aldehyde. Carbonyl group, you know, is you have an aldehyde as well as ketone. So out of them, it is an aldehyde. This was proved by the fact that when you treat glucose with aqueous bromine. Now aqueous bromine or bromine water is a mild oxidizing agent. So the CHO group, aldehyde groups gets oxidized to carboxylic acids. Okay, aldehyde group is such a group that it easily gets oxidized to carboxylic acid. So this suggests the presence of a easily oxidizable CHO group. So that is how it was obtained. Next is, if you treat it with a strong oxidizing agent like nitric acid, in that case, it produces a dibasic acid. It produces a dibasic acid. Why is it a dibasic acid? Because both the CHO group as well as CH2OH group, they get oxidized. So what does it show? It shows the presence of a primary alcoholic group. Again, another thing is primary alcoholic groups get oxidized to carboxylic acid, not the secondary. So since you get a formation of saccharic acid, that is 2 carboxylic acid groups at the terminal position. So it shows that one side we already know is CHO, the other side is a primary alcoholic group. So this further is confirmed that when you treat gluconic acid, which was formed over here, what is this? This is gluconic acid. So this, when treated with HNO3, this also gives you saccharic acid. So both of them again confirms the presence of a primary alcoholic group. So next is this, later on Fischer gave the structure of glucose, which contains, based on these evidences, he gave the structure of glucose based on this same reactions. So what was this? It contains 6 carbon atoms. So when we draw Fischer projections, always remember the most oxidized carbon is written at the top, or in another way, the carbon which has the lowest locate, that is carbon 1, okay, that is on the top, and the chain is drawn in a vertical fashion. So this is how we get, and these were the location of OH and the H. So as you can see, in all the carbon atoms, the hydroxyl groups are present on the right hand side except in carbon 3. So this is how you can remember the structure. In carbon 3, it is on the other side. Hydroxyl group is present on OH, on the left side. So after this structure was given the configuration D. Now these D and L configurations are theoretical configurations. Okay? Or we also call them absolute configurations. Which are not obtained experimentally, we give them theoretically by comparing the arrangement of the OH on the last chiral carbon. Now, if I see how many chiral carbons are there in the chain of glucose, there are 4 chiral carbons. You can see over here, second, third, fourth, and fifth. So accordingly, glucose forms 8 pairs of enantiomers. It forms 8 mirror images or 8 pair of mirror images. Out of them, which is the glucose that is found in nature? It is this one, in which you have this arrangement of OH group. Now this glucose molecule will also have a mirror image. So whether it is D or L, that is obtained by comparing the configuration of the last chiral carbon. If you compare the configuration of the last chiral carbon, this one, with that of glyceraldehyde. Glyceraldehyde is the smallest molecule of the monosaccharides. So if you compare it, in D-glyceraldehyde, which is dextrorotatory, the OH is present on the right side. The OH is present on the right side, and in glucose molecule that is found in nature, again the OH is present on the right side, on the last chiral carbon atom. So this is given the configuration of D. Okay, so we call it D positive glucose. So this D configuration, capital D, doesn't mean that it is dextrorotatory. The molecule might be levorotatory. This is by chance, this glucose is dextrorotatory also. So if I show you the mirror images of the 2 glucose molecules, so this is D glucose, this is L glucose, which is exactly the mirror image of this one. So L glucose, what do you have? You have OH, which is present, OH group which is present on the left side. So that is compared with L negative glyceraldehyde. L minus means it is the levorotatory. L minus means it is levorotatory. Okay. So it can be the other way around also. D might be minus in some molecules, for example in fructose. It can be the D isomer, D configuration is a levorotatory one. So of course the other one will be dextrorotatory. The mirror image will be dextrorotatory. So this is how we find the absolute configurations. Okay. So after that, this structure of glucose which was obtained or it was given by Fischer, it is known as Fischer projection, in which, as I said, the molecule is always written vertically. Carbon chain is drawn vertically with the most oxidized carbon at the top. Next is this structure was found to be not exactly correct. Why? Because Open chain structure could not explain the following facts. In fact, there were more facts, so I've written them according to the NCERT. Number one, glucose does not react with NaHSO3. It does not react with NaHSO3. Okay. Whereas aldehyde groups generally react with NaHSO3 to form the bisulfite adduct. This doesn't happen in glucose, although it has an aldehyde group. It does not give the Schiff's reagent test, that is a test of aldehyde group. Pentaacetate of glucose does not react with hydroxylamine. It does not react with hydroxylamine to form an oxime. Although glucose itself react with hydroxylamine to form oxime, we have done this reaction over here, but pentaacetate does not do it. This does not react, although CHO group is free, okay, according to the open chain structure. So what does this indicate? It indicates the absence of free CHO group. It means the CHO group is not free. So glucose is also found to exist. It is also found to exist in two isomeric forms, that is L-glucose and alpha glucose and beta glucose. Two isomeric forms, alpha glucose and beta glucose. What is the difference between them? What is the difference in their properties? The melting points are different. One is 419 kelvins, the other one melts at 423 kelvins. Then their optical rotation is different. Alpha glucose has an optical rotation of plus 111. Beta glucose has an optical rotation of 19.2, plus 19.2. They are formed by the crystallization of the solution at different temperatures. So this is at 303, this is more than 371 kelvins. And in fact, if we dissolve any of these isomers, let's say I dissolve alpha glucose in water, you get an equilibrium mixture which contains both alpha and beta. And even if I dissolve beta glucose in water, so that also forms an equilibrium mixture that we can ascertain by finding the optical rotation. Because alpha glucose optical rotation decrease, whereas in beta glucose, if we dissolve, the optical rotation of the solution increase, and ultimately it settles at 52.5 plus 52.5. So what does it mean? Ultimately, you get the concentration of both of them in the solution. Ratio remains the same. So what is this due to? It means that glucose does not occur always in the open chain structure. It forms a cyclic structure, and that is very reasonable. Why? Because glucose contains hydroxyl groups as well as an aldehyde group. And we have done in the chapter of aldehydes and ketones that hydroxyl groups, alcohols, react with aldehydes to form hemiacetal, which is followed by the formation of acetal. So why not over here? So if this acetal is formed by the acetal is formed by the reaction of OH group on the fifth carbon with the aldehyde. The lone pair on oxygen attacks this carbon, whereas pi bond changes, pi electrons shifts to the oxygen, and this hydrogen gets attached to this OH, resulting in the formation, remember this is carbon 1, resulting in the formation of two isomers. This is again carbon 1, this is carbon 1. Since aldehyde group is a planar group, the new OH group that is formed by this reaction of H with OH, you get OH. H with O, you get OH over here. In this case, you get OH over here. Because the attack can occur from both the sides. So if we get OH on this side, on the right side, the resulting molecule is known as alpha D positive glucose. This is alpha D positive glucose if OH is present on the right hand side, the new OH. And if the OH which is formed is obtained on the left side, we call it beta D positive glucose. Optical rotation remains the same. So This is what, this is a hemiacetal. Which form it is? It is a hemiacetal form of the glucose molecule. So due to that, we are obtaining two isomers, okay, and in the center you have an open chain structure. So as I showed before, if you dissolve any one of them in water, ultimately you get the same equilibrium mixture. Why? The closed chain structure, the cyclic structure, open ring opens in the solution, forms an open chain structure which again cyclize. So this continues. That is why you get the equilibrium mixture. Now, how do we draw the structure in a cyclic form? Since it is a cyclic structure, you can make a ring out of it. This method was given by the scientist Haworth, and it is known as Haworth's projections. Haworth's projection of Haworth's structures. So in this structure, what do we see? How do we make it? The glucose molecule will form a 6-membered ring, out of which there will be 5 carbons and 6 will be oxygen. So if I draw it over here, if I draw these projections over here, so this is the ring structure, 6-membered ring, carbon 1 over here, 2, 3, 4, 5, and carbon 6 will be this one. And rest of the groups, rest of the functional group or hydroxyl groups are arranged in such a way that the groups which are present on the right side are drawn below the ring, and the groups which are present on the left side are drawn above the ring. So C1 OH is on the right side, so I draw it below the ring. Okay, again you can see C2 OH is again on the right side, I draw below the ring. C3, it is the opposite. So this is how I draw it, OH, H. C4, if you see, OH is again on the right side, so that is drawn below the ring. And so on. So this is known as the cyclic structure, and the full name of this structure, alpha D positive glucopyranose. It is written as alpha D positive glucopyranose. Why pyranose? Because this structure is compared with the 6-membered ring, where in the sixth position you have one of the positions occupied by oxygen. So this is pyrene. So from there you get this name, pyranose ring structure. Similarly, if I draw beta D positive glucose, 6-membered ring, so carbon 1, 2, 3, 4, this is 5, hydrogen over here, and this is carbon 6. So the same way, what is the difference in the two? In this case, the OH is present on the left hand side, so I have to draw it above the ring. Right side below the ring, left side above the ring. Okay, the difference will be, yeah, this is H, second carbon, OH. Rest of the groups will have the same arrangement. Rest of the groups have the same arrangement. So this is beta D positive glucopyranose. Beta D positive glucopyranose. So what are such? Now you again have two isomers, formation of two isomers. One is alpha and beta. Same thing over here. What are such isomers called? These isomers are known as anomers. They are called anomers. So if you define anomers, okay, are the isomers which differ in the position of the functional group of functional group. In this case, it is hydroxyl group around carbon 1, C1, okay, around the first carbon. So that is the only difference in the two. So such isomers are known as anomers. Okay. So with that, I finished this session. Okay, we are completed with the, okay, and bye all of you. Have a nice day. Stay safe also.